Hi, my name is Shah Nawaz. In this lecture, we are going to introduce the notion of subbasis for a topology. But before that, let us recall what we did in the last lecture. So, in last lecture, we did a result regarding the basis for a topology. So, if we have a set X, so X is a set, and say this fancy B, this is a basis for a topology, say T on X. So this B is actually the basis for this topology on X. Then this T is then the result says that this T is actually the collection of all unions of elements of B. So this T is actually the collection of all possible unions of elements of this fancy B. I mean an element U belongs to tau, or we can say this U is an open set of X if this U is actually some union of elements of B. So this was the first result, and the second result was that if we have a set X and we have two bases, say B and B prime, where this B generates a topology T and this B prime generates a topology T prime, then what we did in last lecture, we proved that this T prime is actually finer than T if and only if we have any element X in X and a basis element B in B with X in B, then we should be able to find a basis element, say B prime in B prime, such that this X is contained in B prime and this B prime is contained in B. That is, this topology T prime is finer than T if the basis element of this T prime are actually smaller than the basis element of this topology T here. Now we are going to define a topology on R, which we call the usual topology or sometimes the standard topology, and the definition is as follows. So we have the definition of usual topology. So let say this script B be and the so B the collection of all open intervals in the real line R. So I mean, i.e. this B is actually the collection of all upper intervals AB, where A and B are real numbers. Now by open interval AB, I mean the set of all real numbers X such that this real number is strictly less than B and this X is strictly bigger than A. So this is the definition of open interval. Then this B serves as a basis for a topology, say T on R, that we call the standard or usual topology. So then B serves as a basis for a topology on R, which we call the standard topology. Or sometimes the usual topology, and which we denote by say TU, where U stands for usual topology. Let us first see whether this B serves as a basis for some topology or not. So this B is a basis for this TU if this B satisfies two conditions, i.e. for any element x in R we should be able to find an element in B. I mean we should be able to find an open interval AB in B such that x is in AB. So this is obviously true because for x in R there exists this open interval, say x minus epsilon and x plus epsilon. Obviously this open interval contain x such that x is in this interval. And if we have two intervals, so if x belongs to the intersection of two intervals, say we have two intervals a b and cd, so let us assume that the minimum of CD is E, and say this is F, and maximum of AC is say E, then we can find, so then there exists and this open interval EF in B such that this X is in EF and this EF is contained in this intersection, or in some sense this is we can take this interval here, E plus epsilon and F minus epsilon, and then this E minus epsilon, then this E minus epsilon. Note that this epsilon is a positive real number, and F plus epsilon is obviously contained in this intersection, AB intersection CD. Sorry, this is the containment here. So it is like this. So we have the interval, say a open interval A B, and this is the open interval, say C D. So this is A B C D. Then the maximum of AB is B, and which we call the E, and the minimum of CD is here C, which we call F. So x is somewhere here in this, so we can find an epsilon here such that e minus epsilon and f plus e plus epsilon and f minus epsilon. So this will be a small interval here which contain x and which is in the intersection. So this V serves as a topology on X. So then this B serves as a basis for a topology on R, which we call the standard topology or usual topology, denoted by T sub U. Now also if we look at the collection, also the collection of semi open intervals in R, so let us call this collection B prime. So also the collection B prime of semi open intervals in R, that is this B prime actually consists the semi open intervals like this A B, where A and B are real numbers. This also serves as a basis. So this also serves as a basis for a topology on R, which we call the lower limit topology. On R, denoted by say tau L. So again this B prime serves as a topology because if we look at any point, say X in R, we can always find this semi open interval X minus epsilon comma B comma A, while this A is bigger than X. So this interval contain X here and is contained in R. So this B prime satisfies the first axiom for basis. Obviously it is easy to see that it also satisfies the second axiom, i.e. if X is in the intersection of two semi-open intervals, then we can find a semi-open interval which contain X and is contained in the intersection of those two intervals. Now we claim here the lower limit topology is actually finer than the usual topology, but we did earlier a result in the previous lecture that T prime is finer than T if the basis element for T prime are smaller than the basis element for this T. If these basis elements are contained in the basis elements of T prime. So to prove the lower limit topology is finer than the usual topology, it suffices to prove the basis elements for Tu are actually bigger than the basis elements for Tl. In other words, it suffices to prove that these basis element for this lower limit topology are contained in the basis elements of Tu. So let us make this a lemma. So the lower limit topology Tl on R is strictly finer. Now there is this term strictly finer than the usual topology, say tu on R. So let us prove this. So we know the collection, so we know the collection, and this B which contain the open intervals B is a basis for this usual topology, and the collection B prime which consists the semi open intervals this is a basis for the lower limit topology TL on R. Let us write down here that this is a basis for usual topology Tu on R. Now to prove this, what we wish to prove? We wish to prove this lower limit topology is finer than the usual topology. So to prove this, it suffices to prove so actually we are going to use this result here. I mean, we are going to use this result here. So if we have topology T and we have topology T prime here, and we say this T prime is finer than T, say suppose we have B a basis for tau and B prime a basis for tau prime. So if tau prime is finer than tau, then we should be able to do the following. I mean, if we are given any element x in X and a basis element B in B with this condition that X is in B, then we should be able to find a basis element B prime in this B prime such that this X is an element of B prime and this B prime is contained in B. So we are going to use this result here. So it suffices to prove that for any element, say X in this set R, and any for any X in R and B in this B containing X with, let us write this, with X in B, we should be able to find B prime in B prime such that this X is in B prime and this B prime is contained in B. So actually it is so it's actually easy to prove, since so if we have X in R, I mean for X in R, we have the interval uh, AB in B with, so if this is the given, then there exists this interval xb in B prime such that this x is in xb and this xb is contained in AB. So this is the interval AB here, and we have x an element in this interval, so x is somewhere here in this interval. So this interval is actually the basis element of B. So for this basis element AB which contain x, we were able to find this element here, I mean this element xb, which is a basis element for B prime with this condition. So this means TL, so this shows that TL is finer than TU. Now we had to prove it is strictly finer, so we had to prove it is strictly finer. I mean we had to prove there is some open set in TU which is not in the, I mean we have to find an element say B in TL such that this B is not in TU. That is what we have to prove for this strictness. So on the other hand, given a base element, so let us pick a basis element say xt, so this is a basis element in B prime such that so if this is a basis element in this B prime, then we cannot find, so then there exists no basis element say AB in this fancy B such that this x is in the basis element AB and this AB is contained in xt. So this is not possible because this x is somewhere here. So this open interval AB, we have x here, so this open interval is not contained in this portion because this is obviously bigger than this thing, so this won't be possible. So this proves that hence TL is strictly finer than TU. Now there is this question that now we have two topologies on R. So we have R equipped with the lower limit topology, and we have the same set R equipped with the usual topology. Now a basis element, I mean an open set here will look like an interval AB, or sometimes an open set in R will look like the union of open intervals. Now since this is contained there, that means every open set in TU is also open set in TL. Now there is this question that how can we embed, I mean how can we see this element there, because since TU is contained in tau L, that means this open interval AB has to be open in TL. In other words, we have to show this open interval is actually union of open sets in TL. So one can obviously see that. So this is the, so if we look at this open interval here, so this open interval is actually union of these intervals. So a plus 1 by n b. So note that this is an infinite union of open sets in TL. So if we look at this union over here, this equals this set here. Now since TL is closed under arbitrary unions, so this is an open set in TL, and we are able to express this open interval here as union of open sets there. So that means this is also an open set in TL, because this element over here, this is in TL. So hence this open interval AB is in TL. Now this open interval over here is actually like this. So we have we have A here and we have B here. So this is A plus 1 by n B. So if we substitute n is equal to 1, this is A plus 1. If we substitute n is equal to 2, then we have A plus half. So that will be here. So by taking n to infinity, we will get this interval here. Now there is a question. So a question arises at this point. Since the topology generated by the basis element is, say, B, may be described as the collection of arbitrary unions of elements of B, because this is the definition of the topology generated by the basis. So if we have a set X and T a topology, then we say this T is generated by this basis B if this T equals to the collection of all unions of elements of B. Now there is this question that what happens if we start with a given collection of sets and take finite intersection and then arbitrary unions. So this question leads us to the notion of a subbasis for a topology. So this is a definition for a subbasis for a topology. So a subbasis is actually, so a subbasis, say this script S for a topology on X is a collection of subsets of X whose union equals X. I mean, if we take the union of elements of S, where this S is in the script S, so this union is equal to the X, then we call this fancy S to be a subbasis for X. Now the topology generated by the topology generated by this subbasis S is defined to be the collection of all unions of finite intersections of S. So this is defined to be the collection of all unions of finite intersections of S. So what do we mean by this? So if we are given a set X and we are given some subsets in X. So what we have to, so we, this collection of subsets is the collection S here. So this collection is actually these subsets here. So now what we have to do, we have to generate a topology with the help of these elements in S. So what we do first, we first so suppose these are S1, S2, S3, S4, S5, S6, so on. So what we do first, we take all possible finite intersections. So we take like this, so S1 intersection S2, or n intersection SM intersection SM plus 1, so on, intersection S, suppose T. So this is another element. So like this we take all intersections of elements of S. Then we get some other collection, say B. Then this collection contain subsets of X, and each subset is a finite intersection of elements of S. Now what we do after that, we take the all possible unions of elements of S. Then those sets will be the open sets of X. I mean those sets will form a topology on X, and that topology is called the topology generated by this subbasis. So actually we should check whether this T is a topology on X or not. So let us make this another lemma. So let X be a set and fancy S be a sub basis of some topology. So this is sub basis for a topology on X. Then what we have to prove, we have to prove this S generates a topology. I mean, so this topology is defined to be as, so this subbasis be a subbasis for a topology on X defined. So that is called this topology tau on topology T on X. So defined as the collection of all unions of finite intersections, of all unions of finite intersections of elements of S. So this is what we have to prove. So so what we first take, we take the fancy B to be the collection of all finite intersections of elements of S. So prove. So let so let B be the collection of all possible finite intersections of elements of this fancy S. So then the collection of all unions of finite intersection of S is the collection of all unions of elements of B. So then the collection of all unions of finite intersections of elements of S is the collection of all unions of elements of B, because B is the collection of all possible finite intersections of S. So if we prove B is a basis for T, then we are done. So if we prove B is a basis for T, then we are done. So by that lemma, because the topology generated by the basis is defined to be the collection of all unions of elements of the basis. So let X belongs to X. So if X is an X, it belongs to some element of S. It belongs to some element of S, because S consists of the subsets of X, with the condition that if we take the union of all these subbasis elements, so it is actually the whole set. So if X is in X, so this X has to be in some S in this fancy S. So if this X is in some element of S, so it has to be in some element of B. So and hence to an element of B, because this B is actually the collection of all finite intersections of elements of S. So we were able to prove the first condition for basis, i.e. if X is in some element of X, we are able to find an element in B such that X is in B. So this is the first condition. Now to prove second condition, so this proves first condition for B to be a basis for tau. Now to check the second condition, let X belongs to the intersection of two basis elements, I mean two elements B1 and B2 in B. Then this B1 is actually the intersection of elements in S, where these SI's are in fancy S, and this B2 is S1 prime intersection so on SM prime, where SI primes are in the collection S. So let us take B3 to be the set. So this is also a finite intersection. So then B3 belongs to B, and this x is in B3, and this B3 is equal to B1 intersection B2, and hence a subset of B1 into B2. So this proves the third condition, I mean the second condition for this fancy B to be a basis. So hence B is a basis for tau on X. So actually here we have to prove the topology, I mean this T generated by this way is a topology. So this was a proof.